Hello, everybody. I want to talk today about lifelong learning, which is a method of AI that we use to gain a more reliable AI. So when we look at AI today, there's a lot of confusion because on one side, people use deep neural network, deep learning, and we are told that this gives us superhuman power. And we see that it does very well on playing games and identifying some images and sometimes finding details in images. But once we take this AI and we want to use it outside, like for surgery or for something that is just outside the screen, this is not working so well. In fact, we get some kind of non-trustworthiness when we take this AI outside. And the question is why is it? The issue is that is the answer for most of the issues of current reliability is that AI is frozen after programming or training. So we use today for neural network to provide a very large data set. And this is, then we train on it. We can also take some parts and programs. So we can have combination of programming and training. But either way, once we finish to set this AI to work for us, we cannot change it any longer, that's it. This is very different than any kind of intelligent systems. I mean, think about a person that learned very well until the end of second grade. It was very intelligent until then, but if it's stuck after that, this is a problem. So why is it such a problem for AI? In reality, when you take this AI outside of the screen and the particular games, there is no way to prepare the training set for any possible futures, for any possible eventuality. So there will be malfunctions for sure when the AI meets things that are different than what it was trained for. And in fact, it is very easy also to attack such systems that are not changing. So if we want to think about current AI as one that improves, so the performance is the y-axis, the time is the x-axis. So you see the current AI is improving all the time in training, and that's it. So now if there is a surprise, it will just fail. The type of AI we're talking in lifelong learning is this AI that is all the time aware of how we're doing. And once it's realizing that something doesn't work so well, it opens up. So it has this awareness and it opens up to continue training on what happened. So it means that if we are in a situation, in driving car or in surgery, and there is something that is a question, immediately it open up and continue training. So because of that, I started 3 years ago a program in DARPA that is called Lifelong Learning Machines. And I'll just mention the few of the main pillars for lifelong learning. So the continual learning, that is, we expand our knowledge. We're not stopping at second grade or at the end of training data. We open. So if we do some work, we take this work in the background, we use it for our expanded knowledge. The second one is what we call internal exploration, or what if. And the point here is that, like intelligent system, we cannot only be built on this is the input, this is the output. This is not very intelligent. But what we try to do is to give ourselves all kind of cases that almost happen, that are similar to what happened, and ask questions and train ourselves on many more options than what we saw. So we actually expand knowledge, not by seeing them, but just going outside of what was given to us in advance. The third feature is context modulated computation. And the point here is that if we learn how to do a particular operation, we can do that under small variations. So we don't have to retrain ourselves every time for very small variation. We just modulate what we learned. And what we want at the end is to have this ability to have new behavior, better behavior, and more trustworthy AI. So let me tell you just a little bit on each of these. So before we started the lifelong learning, there are various methods called the continual learning. Some also call them lifelong learning, some will work, but I'll tell you what's the difference. So what they did is they learned it task by task. And the notion that in machine learning is that there is a very interesting feature. If you learn one task and then another task, and you use neural network, any kind of deep learning on neural network, and in fact, almost any type of training on neural network, what you'll have, if you learn the second task, you may catastrophically forget the first task. I'll tell you what it means. Let's say that you had a self-driving car trained on a few billions of examples, and now you had unfortunate accident, and you want to take these 1,000 recent frames and add it just to train the system on what you just saw. So you'll not have that type of accident related to sun and some direction ever again. If you take these 1,000 frames and you take the neural network and just retrain on that, the network will know the recent one, but it may actually forget almost for all of its previous training. So we don't have this option in neural network to take just the new version and to train on that, because you may have catastrophic forgetting. So it means that naturally we don't have in AI these lifelong learning features where we all the time add information. So the notion of continual learning that we started and is the first item in lifelong learning is that, let's say that you have one task and then you learn another task and a third task. How can you keep this task in? Learn, let's say, to separate between ones and zeros. This will be task one. Then you learn to separate between twos and threes. This is task two. Then you learn to separate 4 to 5. This is task 3, and so forth. So there are all these previous methods, elastic consolidation, and so forth. And if you see the task number and the accuracy, you see that if you don't do this continual learning, you forget previous things. And if you do the previous ones, you do very well. You manage to remember at least 5 different tasks. However, in continual learning, what happens is you can separate well between 0 and 1, but there is no way you can separate between 5 and 2 or 6 and 3, because they're not in the same task. In reality, not only you cannot do that, but these methods of continual learning make you not able to do that. So you can repeat exactly the task that you learn, 0 against 1, and you cannot really learn the class. So in order to have class incremental learning, which means if you will learn this task and this task, then at the end, I'm able to see a letter and say this is 7. In order to do that, we are talking about class incremental learning instead of task incremental learning. So it's no longer continual learning. We're going here to the continual type of lifelong learning. And when we try all the previous methods, we say they're failing just very nicely, as if we had none, as if we had no ability. And we need to do something here in order to stay here. So I'm just going to show you recent work. It was published in Nature with 2 people from Baylor School of Medicine. And we had the following understanding. So in a human learning, we have the model and we have the data that we train on. And, you know, if we had the ability to keep the data, then when we had a new thing, we had this accident that I just mentioned, then we take all the previous data and the new data and combine them and retrain from the beginning. So this is like a classical idea of thinking about retraining, but it doesn't really work for AI and for neural network. The point is that we're not going to keep all of them. Otherwise, we really didn't do the trick and then go for another 8 to 9 months and retrain the system. We don't want it. We want to learn very, very fast. So the second idea is to have generative replay. The generative replay is very much like dreams. So instead of remembering all the storage data, we built a generator. And in this generator, I can say, you know, give me an example of a sun in my face. So it will generate to me some input and I will add it here. So what we can do once we learn, we want to learn new things and we don't want to forget the old things. What we do, we prepare the new thing. We prepared very few, some small numbers of generated examples. would have been that without we doing that would be kind of lost, and we train the system. So there are a few issues with that of how we do it cheaply. Also, generating systems are problematic. So maybe it is like dreams. We get things that are a little bit far from reality in some way, to the point that it's not working that well. So the third point is the brain-like way in which we generate abstraction and replace. So we don't generate input, but we generate abstraction. And so the idea will be we use the same network, not one for learning and one for generating. We have like one network. And when we want to remember previous one, what we do is we go to this part here and we run it back in the same network, just very few layers, and then train back. So we didn't train all the way from the input, but only from the end. So we did just kind of a hippocampal-like training. And the good thing about it is once we do that, you see we get very, very bad images. It's really hard to say what letters they are, but it doesn't matter because either way we get something that we wanted. And this is this ability to remember things for over time. So this method, for now, the brain-inspired replace is the state-of-the-art kind of way of continual learning, of lifelong learning version. I mentioned also internal exploration, and I want just to explain a little bit more what I mean about it. So internal exploration is the notion that we have self-modeling of what the AI is doing and what the environment is like. So if we had like this robot arm, and the robot arm needed to take pieces of small balls and put them on the side, you see the shaded arm. So the shaded arm is the model, and it starts very bad. You really don't do what you're doing, but then you start doing it. And once you do that, it gives you a lot of robustness. So if you added another piece to the arm or something changed in the environment, either way, it will take you very fast to just change your internal model and continue working. So this is very useful. Another way that we work on internal replace, so we can take, let's say, images, and I'm taking an image that was given to me. And it doesn't matter that it's not labeled, because in reality, it's very hard to get labeled data. So I can take image that was given to me, I can cut a piece out and say, well, what was supposed to be here? So even that I didn't get any label on the image, I created from an image a labeled data set because I know this is the answer and this is the question. I can take this image and take off the color and say, are these the right colors? Maybe I need other colors. Or another type of internal exploration, I can take many, many images, many scenes, and say, you know, this is a reference image. I see here a train. Which of all these? And just the fact that we can start identifying that many times we see a train station in the same scene with a train teaches us a lot about what this station is about. So these are the type of internal exploration that we do. This is what we do in the back in order to better understand what we went through. So we model us, we model the environment, we try to ask questions to understand better what's the meaning of how things are correlated. Now, when you want to evaluate lifelong learning, you cannot just take a fixed database and compare it to something. You know, it's really very wrong, because the whole notion of lifelong learning that you're able to do things that you were not able to do before. So for example, if you take a modified StarCraft 2 interface and you start playing, so in a regular StarCraft, you have a fixed game, but here as you go, you can change the terrain, you can alter the unit capability, move the goals from place to place, and you can even do more. You can start switching between friends and foe, even increase weapon range. So if you do all kind of possible changes, it's very different type of game for the player. So I will have to do something very different if it knows that the world can change. Just by knowing it, it is building itself in a way that is very fast and very aware, instead of just thinking that everything that it's trained on, you can do it with closed eyes. And just to mention, for fun, in the program of lifelong learning, we had a large amount of our money was given to biologists. And because of that, we got some kind of lifelong learning machines made not only in computer and from synthetic material, but also from biological material. So we have a group that got frog skin and created various robots that work for some time with these great features of lifelong learning. We also work with people that are doing synthetic biology and using some of the same features into AI, which is really all new world. Okay, so for us, just to recap, how do we want to make lifelong learning super reliable, or AI super reliable? So the first thing is we can't rely upon what was trained in advance. What was trained in advance is very good, and it's good for some word. It's not good for words that can be dangerous. We don't want to work in black eyes and static thinking. We want AI that when it's work, it also can take this experience that it works and injecting it in, so it's aware and it all the time expands its capability in a good way. The second feature is that we want to have systems. We're talking about a second program that is called GUARD program, or Guarantee AI Robustness Against Deceptions. And in the field of government, and perhaps even in medicine, we want to make sure that nobody is playing with our AI from far away or make us do wrong things. So actually have a way to train the AI and to build the AI structure from the beginning so that it's robust. If we don't do it from the beginning, we cannot fix it later on. It will be too late. It will be just like running after something that is changing. Then there is a third feature, and this third feature is human in the loop. So it's really saying that the AI is autonomous and we kind of almost fully relied upon it. But in areas that are very important for us, we still want to have many times a human in the loop. And the question is how we do it in the way that the human is not just sleeping there because it knows that the system will always do things, but it keeps him mildly engaged in times and in a way that does not affect cognitive load, that it can actually be very awake and very useful when it's needed. And for this, we have some work in my lab about human in the loop. In fact, we just got a patent approved for some work in this area. Then the next one is we want to have environmental awareness. And when I was in DARPA, we're talking about environmental awareness in different ways, like AI that is aware of time, how long things take. Are there features that are coming back in some periodicity? Are there other features of the environment? Is it possible that there are changes in conditions of weather that make things different? So this kind of environmental awareness, when the AI is aware of that, we tweak things, as we said in the lifelong learning, under modulated computation. So we modulate the computation when the AI is aware. And the last part, which is very important, I think, for reliable AI, is to have this partnership between symbolic and sub-symbolic information. So what we have in neural network is what we call sub-symbolic. And when the human is behavior and the system is capturing it, it is in a sub-symbolic way. But if a partner, a human, wants to say something to the system, it does not want to create a few thousand examples. Sometimes it has 2 sentences and that's it. So this in the incorporation of symbolic into the network will be something that is of great use. So this is just a slide from the GUARD to say that explainable AI and computed confidences are not the answer for guaranteeing AI against deception. You need to do smarter things. the human in the loop in a way that you can take different screens and make the human look every time cool in one place without affecting its cognitive load. And for here, this is just the summary page in which I want to suggest that perhaps in a few years, much of what we call today AI will not be considered intelligent at all without this feature of lifelong learning. So for example, if there is a prosthesis, you want it to come trained and programmed from the factory, then you want to give it to the wearer so that it will be really adapted by the wearer features. And then you want to leave tiny bit of awareness, because even the person who wears this prosthesis may go on a different kind of floor, different kind of lawn or any other snow condition or rain condition in which things are different. So in this case, you want to give it just the one more awareness to never really go to sleep and just do what it was told in advance. And with this, I want to thank you very much and hope you enjoy the rest of the conference.